Alright, so this is problem number 11. Problem number 11 says something, but I'm on the wrong page. Give me a sec. Okay, so problem 11 says that there is a rocket in outer space. Okay, and at time equals 0, it starts the engine with an increasing force equal to F equals AT squared. Okay, it's like that. Where T is time, and yeah, and then A is just a constant. So then it gives us that for F of, what is it, 1.25? 1.25, so when time equals 1.25, the total thrust equals 781.25. And then it wants us to find A, the constant, this guy right there. So, to do that, that's just algebra. Pretty simple. So we're going to go ahead and move on to the next one. We'll get back to that in a sec. Right, yeah, okay. So to solve for this, you take your stuff here, and you square that because you put that into the equation. So you can basically end up getting 781 that's just 1.25 equals A, and then that's 1.25 squared. This comes out to be what is that? 75, I think it's like 125 or something like that. It's be a fourth times a fourth, which is an eighth. So yeah. And then you divide this by that, so the 1.125, and that equals 500, which should be the answer for that. So I'm going to go ahead and erase pretty much all of this and just put that up here. So it's 500 T is equal to the force. So then it asks us in part B, what impulse does the engine exert on the rocket during the 1.5 second interval starting at 2 seconds after the engine is fired. So the impulse is the force over time, or it's the integral of force dt. Yeah, so that's that. So we're just going to integrate this in regards to t. And then our bounds are going to be from 2 seconds, because that's when it starts, to 1.5 seconds after that, so 3.5. I'll draw the integral sign here, 500 t squared. So it's pretty simple. You just divide everything by 3 and change this 2 to a 3, so that way when you take the derivative, these would cancel out, this would go to a 2, and you have your stuff. So then with this, that's no longer an integral that we're trying to find here. We're just evaluating this guy here from 0, or not 0, from 2 to 3.5. So then when you plug that in, you get 500 times 3.5 cubed over 3 minus 500 times 2 cubed over 3. And when you plug that all in, it comes out to be something. Let me double check my paper. It comes out to be 5,812.5. Yeah, it's really hard to write on that far side. Okay, so that's our answer there. And then it goes on and has a part C, and then it asks how much does the velocity change over this interval. So the way I did this was actually pretty simple. I'm going to leave all this up here because we're actually going to end up using most of this. So force equals mass times acceleration, right? It also gave us the mass of the rocket at the beginning, which is 2150 kilograms, if I can write. So if you take the force, which is this guy here, and divide it by this, which is your mass here, you get acceleration, right? So if you have force, which is 500 t squared over 2150, this equals your acceleration. And then it's asking for us to find the velocity change during this interval. So the integral of acceleration is velocity. And we basically already have this here. The only difference is the coefficient is different. So all of this stuff right here, ignoring the t squared, is just a coefficient. So we can just replace the 500 with 500 over 2150. Or we can just add in the bottom here, 2150, because order of operations, that's legal. So then you just go ahead and add that in there, 2150, 2150, and you calculate that all out, and you get that it is going 2.703 meters per second of change in that time span.